But in our work, or when we are deploying, for distance, specifically in routers, we have a dedicated tool. This tool allows us to adjust the metric value of routing entries. Using this specialized tool, what tool is it? It's called the offset list. Not cheap, it's called an offset list. Yes, it's called an offset list. Offset list. So the offset list is used specifically in distance vector routing protocols, allowing us to modify the metric value of routing entries. Since the metric value in distance vector routing protocols has very distinctive characteristics, it's passed from one device to another device. During the process, it calculates the links along the path, including bandwidth, delay, reliability, load, and MTU. For distance vector routing protocols, when we calculate the metric, we use some parameters of the link. So the offset list is used specifically in distance vector routing protocols. We should say it can only be used in distance vector routing protocols, meaning the RIP protocol and EIGRP protocol can both use offset lists to modify metric values. However, it has one fatal drawback. It can only add to the metric value, but not subtract from it. We can directly use the offset list to modify the metric value of a specific routing entry. But the offset list can only add, not subtract. For example, now, if we reset the entire environment to default, then we go to R3 and reset the delay for loopback 0 to default. No, delete, reset to default. Now, let's go to R1. The routing entry should have returned to a metric value of 130816. No problem. We want to use our offset list to modify the metric value of a specific routing entry. How do we do that? Let's say for R1 now, the routing entry for 10.10, 3.0/24, currently has a metric value of 130816. Now let's modify it. If I want to achieve equal cost routing, as we mentioned before, by default, only one optimal route is stored in the routing table. Unless what? We mentioned a special case before. If two routes have the same prefix, same mask, but different next hop addresses with the same administrative distance and the same metric, then both will be considered optimal routes and submitted to the router's routing table. In the routing table, the router typically stores only the optimal route, preferring the one with the lower administrative distance. For routes with the same administrative distance, it will prefer the one with the smaller metric. So if two routing entries have the same prefix and mask, the same administrative distance, and the same metric, they will both be optimal routes. They can both be submitted to the routing table. This is the origin of equal cost routing. Equal cost routing's origin. For example, if I perform an operation, I want to achieve equal cost routing for the October 3rd 10, 0/24 routing entry. We want it to be able to go up and go down, achieving equal cost load balancing. Both routing entries can be submitted to the routing table. How do we do it? Same prefix, same mask, same administrative distance. I need to make their metric values the same. I need to adjust the metric values. But note that the metric value, if we use the offset list, we can only add, not subtract. So we can only add to the routing entry metric value of 130816 and increase it to 1.31072. It won't cause a loop. Don't worry. Equal cost routing won't cause a loop. What is equal cost? For R1, it means equal cost. For R1, it can go up or down. This isn't a loop. All right. Later, I'll show you the packet forwarding phenomenon. 131072. So, how much are we off by? 65 off by 256. Right, off by 256. Equal cost load balancing. Of course, it won't loop. Take a sip of water, hang on. Lately, caffeine seems to have no effect on me again. I stopped drinking coffee for a while, but now I seem to be addicted to caffeine again. Drinking it doesn't work, but not drinking it makes me sleepy. Without it, I get tired. It's just that kind of situation. I don't know how to solve it, maybe I'll switch to tea. Drink green tea, or chew on chili peppers. Alright, we are off by 256 in the metric value, so we'll do this. First, modify the metric value. Where can we modify it? Notice, with the offset list, we can modify the routing entry in the outbound direction, or we can modify it in the inbound direction. For example, I want to modify the metric value in the outbound direction. How do we do that? When R3 is about to advertise this routing entry, R3, when it's about to advertise this routing entry through interface 0, 1, or through interface 0, 3, to R1, we will modify the metric value of the routing entry in the outbound direction. Note, the offset list can only add, not subtract. We'll do it this way. On R3, first, make sure you remember that with the offset list, you need to operate on a specific list. Operate on a specific list. So, the lists we've learned so far are quite simple and straightforward. What kind of list is it? An access control list. An access control list. We studied it in NA. We use access control lists to filter traffic. Now, we can also use access control lists to match routing entries. Access control lists. We want to match a routing entry. Which routing entry? R3. We want to operate on the 10.10.3.0 routing entry. We can use an access control list. An access list. We already discussed access control lists in NA. We can use access control lists to filter and match traffic. We can also filter and match routing entries. So the offset list can operate on the list. Therefore, we need to use an access control list to match it, to match this routing entry. Then use the offset list to change the matched routing entry. Access list, for example, list 10. We match the 10.10.3.0 routing entry. The permit command means to allow, but it also means to match. So now, access list 10, we've matched the 10.10.3.0 routing entry. In R3's EIGRP process, we can make some modifications. Using the offset list, we apply it to the access list 10 we just wrote. It matches the 10.10.3.0. Routing entry. What can we do? Outbound direction. When I advertise it, we offset the metric value of the matched routing entry. How much to offset? We just calculated it. It's off by 256, right? Off by 256. When it goes out through interface 0, 3, there it goes. When R3 advertises the routing entry through 0, 3, for this routing entry, we increase the metric by 256. Done. Now let's go to R1. Show IP1.1.1.1 topology. There it goes. There are two routing entries for 10.10.3.0. Successor routes. Why aren't they all showing up? Why aren't they all showing up? Didn't get stuck, did it? Let me check the neighbor relationship. Hold on a moment, everyone. It should show them all. The F addresses are the same. Checking the neighbor relationship. Everyone, rebuilding. Show IP 1.1.1.1 topology. What's happening? It didn't show them all. There are two optimal routes. Show IP 1.1.1.1 topology. There, it's just slow. What's the issue? I thought it crashed. Look, two routing entries with the same F address. Both are optimal routes. They both can be submitted to the routing table. What does this achieve? Equal cost load balancing. Look, load balancing. Same prefix, same mask, but different next hop addresses. Both can be submitted to the routing table. Both are optimal routes. Alright students, so on R1, we've used the offset list. When R3 advertised the routing entry, it increased the metric value by 256. That was the outbound direction. Of course, we can modify it in the inbound direction. Now let's remove the offset list on the outbound direction of R3. Remove the offset list. 10 out 256, distance plus 3. Remove. To speed up convergence, we'll take a shortcut. Clearing the neighbor relationship. Typically in a company, we don't do this. If we clear the neighbor relationship, the routing entry needs to be recalculated and it converges slowly. Don't do this. Now, show IP EIGRP topology. Done. It's reset to default, 130816. We can modify the metric value in the inbound direction. We can modify it inbound. Now it's 130816. For the inbound direction, we'll write an access control list. Use this list, list 10, and match the 10.10.3.0 routing entry. Match the routing entry with an access control list. Then, with the offset list, we'll operate on the access control list. For the matched access control list 10, the 10.10.3.0 routing entry. When it is advertised into the R1 router, add 256 to the metric value. Where does it enter from? From 0, 3. Then write a command. To speed things up, we'll take a shortcut. Since this is a lab simulation, we can be a bit rough. In real work, you can wait, and it will sync with the log. There will be sync and the resync log message. So now, show IP EIGRP topology. There should be equal cost routing. It works inbound as well. But keep in mind, if in one direction, for example on R3, we operated in the outbound direction, then in the inbound direction, we use the offset list on the same routing entry. It can be cumulative. For example, on R3, when we sent it out, we added 256 to the metric. Then on R1, in the inbound direction, we added another 256 to the metric. They are cumulative. It's a 1+1 situation. Understood? So, for example, on R1, if we, on R3, also use the offset list on the same routing entry in the outbound direction, offset list, how much is it? 10 out through the path 3. We use the outbound direction on R3 and the inbound direction on R1. They can be cumulative. The metric value will increase by 256 in total. As usual, let's speed things up, check the neighbor relationship, re-establish it, rebuild the EIGRP neighbor relationship, send update packets again, refresh our routing entries. It's a shortcut method to make it converge quickly. Show IP EIGRP topology. We should choose the upper route as the optimal one. The upper route with 131072 chooses R2 as the optimal one. The lower route, since we added 256 to the metric, becomes 131328. It can increase the metric outbound and also inbound. The two can be cumulative, so you must be careful. Choose the right scope of usage. Typically, we use the inbound direction. Students, we generally use the offset list in the inbound direction because what we want to change is our own router selection. So we usually apply the offset list inbound to increase the metric value of the routing entry and modify our own. We modify our own route selection. We won't do any tricky operations, meaning we won't operate outbound. We try to limit the impact as much as possible. We operate inbound to modify our own route selection. So we modify our own inbound metric values. All right, that's what we've just covered. Changing the metric value using the offset list. Next, if we want to achieve equal cost load balancing with two equal cost routes, can we offset on both 0, 1, and 0 RSAC? 3. For R3, regarding the same route, you need to be careful. For example, on R3, router EIGRP 90, we use the offset list on the same route, adding 256. Outbound 256 through interface 0. 1. In that case, show running config router EIGRP. In the configuration, you'll find both commands are effective. On a single interface, you can apply it once. For example, on interface 0, 1, you can apply it once for the outbound direction, and 0, 3 can be applied once for the outbound direction. But if on interface 0, 1, you also want to apply an access control list, for example, an access list, to match, for example, 192.168.23.0. I wrote it wrong. Sorry. Access list 20. I just wrote the wrong number. Match 192.168.23.0. If in the same process, let's say the EIGRP 90 process on the same interface offset list, list 20, out 256 through 0. 3, there it goes. Show running config section router EIGRP, you'll find that on interface 0. 3, in the outbound direction, only one access control list 20 is used. Now, in the inbound direction, for example, router EIGRP 90, offset list, inbound 256 through 0. 3, there it goes. Show running config section router EIGRP. You'll see that on interface 0, 3, one inbound and one outbound can both be used. So, students, when using the offset list, remember this. On the same interface in the inbound and outbound directions, you can only call one access control list. You can only call it once. All right, students, this is our BTC note. You can only call it once. So this is what we just talked about to summarize the key points. On one interface, for inbound and outbound directions, if the directions are different, it's no problem. But if you want to apply two lists in the outbound direction, that's not allowed. You either call access list 20 outbound or call access list 10 outbound. On one interface in one direction, you can only use one list, either list 10 or list 20. You cannot apply two lists on the same interface in the outbound direction. It's not allowed. But on one interface, you can apply one list for outbound and one list for inbound. On one interface, you can use two different access control lists for inbound and outbound. That's allowed. But each direction can only use one list. That's absolute. All right, students, that's it.